A set is a collection of objects. Usually we write it with commas and curly braces. So here's the set 1, 2. We see that surrounding it are curly braces, and in between the numbers are commas. We can give a set a name. This set 1, 2, we name it A. 1 is an element of A. There's a special symbol for that that looks like a little E, and that's just 1 is an element of A. 3 is not an element of A, and we can put a slash through that little e, and we'll say 3 is not an element of A. There is another way of defining sets called set builder notation, where you write a description of the set inside of curly braces to define the set. For example, we can define the even numbers by writing x where x is an even number inside of curly braces. When we write it with a vertical bar, but the bar translates to where. In general, to write a set, we can write x where some description of x, and then every x fitting that description will be inside of the set. We could also define a hand of cards by writing x where x is a set of 5 cards drawn from a deck, and then we have our hands of cards. Set builder notation is best when the sets are infinite because you can't write them all down with commas, and if they're really hard to list, like with our cards, I can't really write all that down inside of a set, so I just use set builder notation to define my set. Sets are equal if they have the same elements, so the set 1, 2 is equal to the set 2, 1, and order doesn't matter in sets because if two sets have the same elements, then they are the same regardless of what order they're in. We also say that sets don't have duplicate elements because the set 1, 1, 2 is equal to the set 1, 2, so you should have just written 1, 2, and we say that sets don't have duplicate elements. A subset is when one set fits inside of another set. To be precise, A is a subset of B if every element of A is within B. For example, 1, 2 is a subset of 1, 2, 3 because 1 and 2 are in 1, 2, 3. The is a subset of symbol looks like a less than or equal to sign, which kind of makes intuitive sense. Sets are also subsets of themselves. For example, 1, 2 is a subset of 1, 2 because everything in 1, 2 is in 1, 2, and that's true for any set. If A is a subset of B and B is a subset of A, then everything in A is in B and everything in B is in A, and then the sets are equal. This is a common technique to prove that two sets are equal, but I don't think we'll be doing too many proofs here. There is a tool called the Venn diagram that is used to visualize sets. Let's define sets S to be 1 through 9, A is 1, 3, 5, 7, and B is 2, 3, 4, 5. To make a Venn diagram, draw circles and a box. The box is just all of the possible outcomes. In this case, the box is the set S. Imagine if we rolled a 9-sided die, all of the numbers that we could roll would be the numbers 1 through 9, so 1 through 9 is the set of possible outcomes. The circles are labeled, and inside of them are the elements of the corresponding sets. There is some overlap in the sets. Notice that 5 and 3 are in both A and B. Just like you can add numbers together, you can add sets together. It isn't exactly addition, it's called the union. A union B is the elements that are in A, or they're in B, or they're in both. It's an inclusive or. The symbol for union is just a big cup. In this example, A union B is 1, 2, 3, 4, 5, 7, and these are red and bold in the Venn diagram. There is another set operation called the intersection. A intersect B is elements that are in both A and B. The symbol for intersection is an upside down cup. In this example, A intersect B is 3, 5, and these are red and bold and in the overlap of the circles in the Venn diagram. The complement of A is elements that are not in A but are in S. The complement of A is written with a superscript C. Here, A complement is 2, 4, 6, 8, 9. These are the elements not in the green circle on our Venn diagram. The set difference of A and B is elements in A that are not in B. This is written as A minus B. You can also say A minus B instead of saying the set difference of A and B, but some people will say the set difference, so you should know that that means the same thing. Here, A minus B is 1, 7, and in the Venn diagram, this is elements only in the green circle and not in the blue circle. There are two special sets, the sample space and the empty set. In our example, S is the sample space. It is also the black box in the Venn diagram. I already said this, but the sample space is just all the possible outcomes. If we had a 9-sided die, the possible numbers are 1 through 9, like in our example. Every roll would produce one of these numbers, and every set defined is a subset of these numbers. There are some special properties of the sample space. A union S is equal to S because A has no elements to add to S in the union of A and S. A intersect S is equal to A because all the elements in A are in S, so the elements that are in both A and S are just all of the elements of A. These statements aren't just true when S is the sample space, but generally true when A is a subset of S. The empty set has no elements. We could write the empty set as curly braces with nothing inside, but the common way is to use a 0 with a slash through it. The complement of the sample space is the empty set. This is because every element is in S, so everything not in S is nothing, which is the empty set. The complement of the empty set is the sample space. This is because every element not in the empty set is the sample space. There are some identities. A union empty set is equal to A, and A intersect empty set is equal to empty set. The formulas for unions and intersections with sample spaces and empty sets that I've shown you are really just special cases of when A is a subset of B. The motivated student can draw two circles, one inside of another, and label them A and B, and try to determine the relationship between unions, intersections, and subsets. De Morgan's laws are formulas for what happens when you take the complement of a union or intersection of sets. I'll put De Morgan's laws on the screen. To remember De Morgan's laws, you take the complement and you bring it inside the parentheses to both sets and flip the union or intersection upside down. Let's see if De Morgan's laws make any sense. Let A be the set of basketball players and B be the set of baseball players. If a person does not play both basketball and baseball, then they either don't play basketball or they don't play baseball. If a person does not play basketball or doesn't play baseball, then they certainly don't play both sports. This shows that the complement of A intersect B is a subset of A complement union B complement, and that A complement union B complement is a subset of the complement of A intersect B. This means that the sets are equal. I explained why De Morgan's law works for the complement of A intersect B. See if you can come up with a similar argument for the complement of A union B. If you're having a hard time understanding the verbal arguments, drawing a Venn diagram might be helpful. When you add three numbers together, it doesn't matter if you add the first two and then the third, or if you add the second two and then the first. This is the associative law for addition. There are also associative laws for unions and intersections, meaning that it doesn't matter what order you take them in. If you have a mixture of intersections and unions, it is not associative. In this case, there's a distributive formula, similar to the distributive formula where multiplication distributes over addition, intersection distributes over union, and union distributes over intersection. To help remember these, you can just pretend that the operation outside of the parentheses is multiplication and that the operation inside of the parentheses is addition. Just like you can draw a Venn diagram for 2 sets, you can draw a Venn diagram for 3 sets. If you try to draw a Venn diagram for 4 sets, though, you're probably going to get in some trouble. I really like drawing Venn diagrams when I'm solving problems. A lot of times, if I don't know a formula or something, I just realize that I could use a Venn diagram, and then I get the solution.